Welcome to AllAboutRx. Today, we are breaking down one of the absolute most fundamental and high-yield concepts in all of organic chemistry, resonance. If you've ever felt like your molecules are, playing tricks on you, which, let's be honest, is the shared trauma of pretty much every organic chemistry student, you are in the exact right place. We're going to cover what resonance structures and resonance hybrids actually mean, review the core rules for drawing valid structures, and explore how positive and negative resonance effects totally shape molecular reactivity. To demystify all this, here is our agenda for today. 1. The resonance hybrid. 2. Core rules and framework. 3. Stability and conditions. 4. Electron mobility order. 5. The mesomeric effect. And 6. Real-world applications. Let's get right into it. Section 1. The resonance hybrid. Let's kick things off by busting a massive myth right out of the gate. Resonance simply describes delocalized pi electrons or lone pair electrons whose bonding really just can't be adequately represented by a single Lewis structure. Because of that, we use individual valid Lewis structures called resonance contributors. But here is the most important takeaway of the day. The resonance hybrid represents the real, weighted combination of all those contributing structures. Think of the classic mule analogy, right? A mule is a hybrid of a horse and a donkey. It doesn't rapidly switch back and forth between being a horse one second and a donkey the next. It's entirely its own unique animal. The resonance hybrid acts the exact same way. It is a singular, true structure, not a rapidly interconverting mixture. And this brilliantly illustrates how benzene actually behaves in the real world. Benzene exists as this singular, highly stable circle and hexagon hybrid. It is absolutely not flipping back and forth between those hypothetical Kekulé or Duor structures. Those 6 pi electrons are fully delocalized over the entire ring. So while individual Kekulé structures might be the major contributors on your paper, that circle and hexagon hybrid is the true, highly stable molecular reality. Section 2. Core rules and framework. Now, what's really interesting about drawing these individual valid Lewis contributors is the strict rule book you have to follow. You are bound by a rigid framework. Every contributor must be a valid Lewis structure, and you have to keep a constant total number of electrons. The absolute crucial point here is that your atoms and that entire sigma bond skeleton are completely frozen in place. You are only ever moving electron placement, literally never the atoms themselves. And because those atoms are locked down, the hybridization of every single atom has to stay exactly the same across every structure you draw. When you're moving these electron pairs, they must only move to adjacent positions using proper curved arrow formalism. Take analyte formation, for example. Your arrows have to start at the electrons and end at adjacent atoms or bonds. You have to avoid those invalid traps, like violating valency. Creating an impossible pentavalent carbon with 5 bonds is pretty much the ultimate cardinal sin of organic chemistry. You also have to make sure your arrows are never, ever pointing in the wrong direction. Section 3. Stability and conditions. Since the hybrid is a weighted average, we have to systematically rank our individual contributors to see which structure actually dominates. You rank stability by running through a quick mental checklist. First, maximize your covalent bonds and look for complete octets. A structure with a full octet on every atom easily outranks one without. Second, seek out fewer formal charges and minimal charge separation. And third, if you do have charges, make sure you are placing any negative charges on the more electronegative atoms. But keep in mind, absolutely none of this happens unless fundamental geometrical conditions are met. Resonance requires that every single participating atom is perfectly coplanar. In plain English, they have to be completely flat like a pancake. They need this flatness to maintain parallel, unhybridized p-orbitals. If the atoms twist out of alignment, the connection breaks. When they're perfectly flat, it allows for delocalization in a conjugated system, whether that's conjugated pi bonds, a lone pair, a charge, or a radical. No coplanarity, no resonance. A perfect example of this is the carbonate ion. It beautifully proves these stability rules by equally distributing its partial negative charges and pi bonds. Because all 3 of these resonance structures are structurally equivalent, they contribute equally to the hybrid. And the result? You get 3 experimentally identical carbon-oxygen bond lengths, each with a bond order of 1.33. That means the bonds are literally a hybrid. They're longer than a traditional double bond, but shorter than a single bond, proving that the real physical structure is indeed the hybrid. Section 4. Electron mobility order. Before we apply all this to larger systems, we really need to know exactly which electrons are most willing to move. We have to look at electron mobility as a strict hierarchy. Unshared lone pairs are basically the free agents of the molecule. They are the most mobile and reactive, meaning they are the very first to get involved. They're followed by pi bond electrons, which are a bit more attached but still willing to shift around. And at the very bottom, your sigma bond electrons. Those are the locked-in foundation of the molecular house, fundamentally maintaining that fixed skeleton we emphasized earlier. And to properly map these electron movements, you must never interchange your arrows. Seriously, doing so is the easiest way to lose points on an exam. A double-headed arrow strictly means resonance between hypothetical Lewis structures. That is fundamentally different from the double harpoons, which represent a real chemical equilibrium. Likewise, a full arrowhead means the movement of an electron pair, while a single harpoon means the movement of just one solitary electron. Section 5. The mesomeric effect. Let's see how this all builds into broader molecular behavior through something called the resonance or mesomeric effect. Functional groups can dramatically alter a ring's reactivity and charge distribution. A positive R, or electron-donating group, forcefully pushes electron density directly into the conjugated system. On the flip side, a negative R, or electron-withdrawing group, acts as a pi acceptor and aggressively pulls electron density right out of the conjugated system. Take a look at phenol. Here, the hydroxyl lone pair acts as a plus R donor. By pushing electrons into the ring, it creates specific regions of partial negative charge, directly at the ortho and para positions. This completely activates the ring at those exact structural points, priming them for reaction. Conversely, look at the nitro group and nitrobenzene. It acts as a minus R pi acceptor. It's forcefully withdrawing electron density away from the benzene ring. If you trace the resulting resonance structures, you'll see this pulling effect leaves those exact same ortho and para positions completely drained, resulting in a partial positive charge at those sites. Section 6. Real-world applications. So why does memorizing this strict rulebook actually matter for your exams and your everyday lab work? Well, resonance analysis is the crucial bridge between abstract theory and chemical reality. Understanding resonance is quite literally your master key for predicting the exact sites of electrophilic or nucleophilic attack, just like we saw with phenol and nitrobenzene. It perfectly explains experimental dipole moments, makes sense of those hybrid bond length equalizations, and helps us fundamentally understand overall molecular stability. Which brings us to the big picture. Once you master electron mobility and these stability rankings, predicting reaction mechanisms becomes completely second nature. It will totally transform the way you look at a synthetic pathway. So, I'll leave you with a final thought to ponder as you head into your next exam or lab session. How will you use these rigid rules of resonance to confidently predict the outcome of your very next organic reaction? Thank you for viewing this explainer. If you found this explanation helpful, please make sure to like, subscribe, and drop a comment below with any questions or topics you want us to cover next. See you in the next explainer.